I kind of wanted to give some high-level overview of some recent exciting kind of directions that we were exploring in our group, and not just our group, and MILA in general. And actually, it's becoming like quite a popular area in terms of scaling, robustness, and of course, generalization being the holy grail of AI, machine learning, and statistics for many decades. Kind of always start all my talks with this because it's kind of still the problem. Everybody is aware of amazing advances in AI, especially in the last decade and especially in last few years, in all kind of areas from game playing and beating human champions in Go and chess and generating paintings that kind of as good or better maybe sometimes than the human paintings because they're being sold for quite a lot of money in New York auctions, and medical imaging being actually done sometimes with superhuman kind of accuracy in terms of detecting some abnormalities and so on and so forth. And of course the recent, well, relatively recent, but by now there is so much that happened since then, OpenAI GPT-3 large-scale language model that keeps improving, and there are many others that kind of also use a scale to improve generalization performances and achieve very kind of dramatic results that people never seen before. For example, DALL-E 2. There is lots going on, but still the same problem that was kind of driving the field for past decades, it still remains that this impressive AI is still somewhat narrow, task-specific, good for particular area, and there is still nothing that would kind of parallel what humans do without maybe beating any champions in chess or Go, and maybe not being able to draw as good as kind of the best ones. We're still able to do something that computers are not quite yet able to do. We are very broad or versatile or general, which means that we can quickly adapt and learn very, very different type of tasks in very, very different type of environments throughout life. And we would like AI to be, in some sense, general like that eventually. And that's what kind of led to the term artificial general intelligence, which still remains a holy grail of the field. And of course, you can define it in different ways, but I prefer to stick to what OpenAI kind of define it as highly autonomous system that outperform humans at most economically valuable work. That's broadness of versatility is across various useful tasks. And of course, we're not going to go into various definitions of AGI because that seems to be always reminding me the classical story about the elephant and 7 blind people trying to define what the elephant is, and everybody disagrees and argues what AGI is. But for all practical purposes, what we could agree on, the word general, the ability to adapt to a wide variety of very different tasks from what you were initially maybe pre-trained on, while actually not forgetting what you learned before, because I will talk about that a little bit. It's one of the problems when you learn continually across multiple data sets, unless you kind of do something about that. Vanilla kind of learning algorithms seem to lead to what's called catastrophic forgetting. Again, at very high level, I just wanted to say that there are many interesting sub-areas that kind of try to get to that point, but we particularly focus in the past couple of years on what's called continual learning. As I mentioned, it's like ability of the system to keep training while the environments are changing, tasks are changing, and being able to accumulate all this knowledge without kind of completely replacing what it learned before. The area of robust invariant prediction is also very important for achieving like practical and safe systems that are robust to either adversarial changes in the input or changes just due to statistical kind of irregularities or basically non-stationarities. And related to that, basically item 2 and 3, the out-of-distribution generalization, that's kind of another name for the area that is concerned with getting systems to be able, somewhat like humans, adapt quickly when situation changes drastically. And last but not least, the most recent trend in the field, which quite a few people are very interested in, well, at MILA as well, is so-called neural scaling laws and foundation models, and I'll definitely talk about that in more detail at the end. This continual learning, again, at a high level, it's the ability, like a human ability to learn throughout a life, acquiring new skills, new information, without necessarily fully forgetting what you learned before. If you learn how to ride bicycle when you're 4 or 5, then you probably still can do that, even if you didn't do it for many years, so on and so forth. So if you have this ability, I mean, well, needless to say, there are many applications of artificial intelligence where such ability will be absolutely essential. You can think about robotics applications. You would like a robot to move in different environments and adapt quickly, like even if it's like, I don't know, outside, inside, on the road, and so on and so forth. And then you, of course, don't want to retrain robot every time when it goes back to previous environment. The self-driving cars, or at least partially self-driving cars, are another clear example where you really need some form of continual learning, because driving on the country road versus driving in the city or on the highway are very different environments, and you need to adapt to them quickly. And you can keep going with examples. And of course, I mean, the last but not least is, for example, medical imaging. You have the data coming from different hospitals, from different patients. There are some similarities there. You want a model that can be trained on this data, and you keep kind of moving it to new data sets, and you still want it to be able to work well on type of data it learned kind of before. So kind of you get the idea. Of course, I'm not going to talk about the very technical details and all the algorithms people invented in the past, let's say, decade for continual learning. But the gist of it is like what you are trying to do here is learning a single, for example, deep neural network. And you have to share the weights in this network across these multiple tasks or environments, like the self-driving car, for example. So what you're trying to do, you're trying to learn it in such a way that you maximize transfer of knowledge. Basically, like if you learn something, it helps you adapt in the future to new tasks, and also minimizing interference or forgetting. So you're trying to learn common set of weights so that model will be easily adapting in the future while still working well on the past, essentially. And again, it all stays high level because the details about how to do that, I'm happy to discuss offline, plus I can point you to papers. But just to give you an idea about the continual learning field, it actually has a long history in computational neuroscience, all the way from like 1950s and so on, when people were always asking the question how our natural neural networks manage to be so plastic and adapt to new situations and still have good memory of very kind of knowledge that you acquired back in your childhood. So stability versus plasticity dilemma, how to go about figuring out how it's implemented in our brains, and how to use those inspirations to create artificial systems that can do the same thing. So the field is, as I said, with long, rich history, but in deep learning, there was exponential kind of blow up in numbers of works on this topic pretty much since 2012-13, when actually deep learning really became popular once the AlexNet improved the results, the state-of-art results on ImageNet, and the whole wave of deep learning research started really kind of booming. Same happened with continual learning. Okay, and kind of, as I said, just to complete that topic, because I want to switch to a few others that I mentioned. You can think about like what you're trying to do during continual learning and what you're trying to get at by analogy again with human brain. We have multiple brain areas and multiple subnetworks which are kind of responsible for certain functions. Well, I mean, it's very crude, of course. Separation things are much more sophisticated, but you roughly can think about well, you have your visual cortex, you have auditory cortex, you have motor cortex, you have prefrontal cortex, kind of responsible for decision making, so on and so forth. So in a sense, you have these somewhat independent subsystems responsible for different functionality, and when recombined, you are able to kind of achieve whatever task at hand that you're getting. And if you try to maybe formalize it in the artificial neural nets, then you can say every data set and training a network from that, assuming that you're trying to predict something, can be essentially viewed as a function approximation. And now you can say that in continual learning, you go through a long sequence of different data sets trying to learn different functions, so that eventually you want the system of finite size that can later on approximate any function that comes its way, even those that you didn't see before. You can say that, well, maybe roughly like a brain, the finite network that can handle everything, we could come up with this set of basis, quote-unquote, functions, subnetworks or mechanisms, and then you can recombine them to solve anything in the future. The hope is that our world is not infinitely complex, at least during our lifetimes. It has some finite basis, so we have a hope of learning it and then recombining those basis components to solve problems at hand. Again, I apologize, I'm staying very high level here, but all the technical details we can definitely discuss offline. The next topic I'll go through very quickly, but just to give the gist what I meant by robustness, invariance, out-of-distribution generalization. Probably many of you have seen this type of pictures many times. The issue with modern deep networks often is that despite being very accurate on the data that they're trained on, for example, I don't know, images like this cat, if those images are perturbed in certain adversarial way, slightly, so you will not even notice, human eye will not detect the difference, but the kind of specifically introduced noise can completely derail deep network, and it will make absolutely incorrect predictions most of the time. So the point is that unfortunately we really have to work more on making those systems robust or stable to all kind of perturbations of the input. So it's like easy to fool them. And there are many methods. It's a whole field called adversarial robustness, and we kind of were very interested in that. We worked with my colleagues at McGill, Poya Bashivan, and Blake Richards and others. And this is kind of recent paper from last New Rips. As I said, it's a huge field. It's our like 2 cents in this direction, but I thought it was kind of interesting that the idea here was if you try to focus on making kind of generic, robust representations of the input, then no matter what task on top of that you will have to solve, that will help you be adversarially robust, as opposed as kind of some state-of-art methods where people try to make the actual predictions robust. We try to make the representations not sensitive to all these adversarial changes in the input. And then you can build on top of them, and you become much more general in terms of what kind of attacks you will be robust to. And the related robustness topic is, well, nothing adversarial. Nobody adds any noise on purpose, but your environment changes, your training data change. For example, the proverbial cows on the beach that was kind of used as an example in this field for last several years. Imagine you're training a classifier of animals, and it happens that most of the samples in the database contain cows on the green pastures. Naturally, that's where they usually are. So your classifier is supposed to learn features of animals and discriminate between animals based on those features. But again, it's been observed many times that deep nets are like lazy students who study to the test only to pass the test on this kind of data. And when their environment changes a bit and you see pictures of cow on the beach, again, the accuracy might be quite bad because those systems selected wrong features, spuriously correlated but easy features like background, instead of the true features related to animal shape, but a bit harder to detect maybe. And therefore, there is this whole field on kind of learning invariant robust representations, invariant robust predictive models. that try to avoid this kind of shortcuts. So basically, they try to push the deep learning algorithms into extracting those features that are truly invariant, say, to that animal across multiple different environments, rather than some easy features that may be highly predictive in particular data set, but they're spuriously correlated. They have nothing to do with that animal. Anyway, so there was just, if you're interested, another paper we had last New Reps trying to analyze properties of such algorithms, one particular famous invariant risk minimization, and understand when it may actually fail and how to improve it, and so on and so forth. Joint work with our amazing postdoc, Kartik Ahuja, and with Joshua Benjo, and with others. So anyway, that was kind of all these attempts to get to general and robust AI. And most recently, I mean, there are various ways to go about that. You can either tweak the algorithms, add constraints that will push the kind of methods to learn more general and fast adapting kind of systems. Or apparently there is a very interesting new kind of wave of research that, again, many of you might have seen. It was very much kind of popular after OpenAI released, well, by now almost 2 years ago, the GPT-3 natural language processing system. And after that, other multi-modal systems, both with language and images. Then also the Copilot system that actually can also produce code, I don't know, Python and so on. So there is this whole explosion of large-scale pre-trained models in unsupervised way that later on seem to be very easily adapted to wide range of tasks. So in a sense, this holy grail of getting more general AI seems to be getting a bit closer through these large-scale pre-trained system approaches. To the point that last August, large group of people in Stanford wrote this like position paper and called them foundation models, because you basically train them on humongous amounts of data, for example, GPT-3 on almost like all of the internet. So there is a very rich source of information. You also scale the model, not just data, so its capacity can match that amount of information. At the end, you have some generic kind of knowledge base or statistical model that kind of knows a lot. And then when you wanted to do specific things it wasn't really trained on, apparently the claim to fame for GPT-3 that it is so-called few-shot learner. You only need to show a few examples, or sometimes, I don't know, maybe even one, of what you wanted to do to give it an example, and it adapts very quickly. So in this sense, it's truly getting closer to what people would call general artificial intelligence. It's something that can be very easily adapted to kind of pretty much anything. I mean, of course, it's not yet perfect. There are many, there are more recent versions that kind of try to improve issues with the systems when they just cannot do properly certain tasks, and they also can output not very aligned with human values type of output, and there is Instruct GPT. So a lot of going on in this field. Of course, I mean, it didn't solve AGI yet, but it's definitely, I think, big step towards it. And it's not just language, as I was mentioning, this also clip system. I mean, there are other systems now that were built on top of that, so the field is expanding. But the bottom line was that as compared to like normal state-of-art systems pre-trained on like large ImageNet and so on, when pre-trained on wide variety of data and when large enough, those systems, even without seeing any examples of some out-of-distribution data set, still are able to do well there, while traditional systems just break immediately. So with all this scaling, the question often is like, but it's OpenAI, Google, DeepMind, and all those kind of companies, they have lots of compute. Microsoft gave like 10,000 GPU supercomputer to OpenAI, and this and that. So people are asking questions, so what do we have to do with scaling if we have like just a few GPUs? And the answer is actually you can do a lot in terms of studying trends of your new or existing algorithms or models, because you don't have to go all the way and train GPT-3, but with relatively small compute even and relatively small data. I mean, you need to figure out what is sufficient, but you can predict trends in behavior, and that can be very important. And this plot is essentially from that paper on visual transformers, where they basically compare state-of-art convolutional networks that for many years were considered the best thing you need to use when you have image data. But then you can compare them with these new models, visual transformers, that do not have this specific inductive biases from neuroscience or vision. They are just absolutely generic. And when the data are relatively small, convnets outperform them as expected. And then you see the trend when you have extremely large amounts of data, their behavior reverses, and visual transformers are clearly better at large scale than those convnets. So this is just one example. What I'm trying to say, the usefulness of neural scaling laws is in the fact that you can compare a few methods, and even if something is state-of-art now, it may not be anymore, while the other method is not as good, if more compute and data will become available. And you want to know that because essentially it's almost like with investment. You need to decide which machine learning direction of research to invest in. And this type of scaling laws can be a helpful investment tool. I probably have to start wrapping up, but I just kind of wanted to give that famous classical example of what was discovered recently, and now there are many more kind of works along these lines. Essentially, that those scaling laws can be surprisingly simple. That this was studied by OpenAI and by Jared Kaplan from Johns Hopkins and his colleagues. They actually now they opened a new scaling and alignment startup called Anthropic. But basically what they discovered, well, not surprisingly, when physicists look at large complex systems such as artificial neural network and try to study as if it was like a statistical mechanics kind of domain, interesting things appear at scale. Basically, what is shown here, it's log-log plot, and straight lines show how the loss, test loss, drops with respect to increase in compute, data set size, or parameters. I mean, there are details about like exactly what it means. It's important here that you do not limit data and model size, but just increase compute, and whatever best result you can get, you plot here. Similarly with data set size, you vary the amount of data available, but also you allow to choose model of appropriate size, larger or smaller, whatever works better, and so on and so forth. Bottom line is you get those empirical laws, power laws, or straight lines in log-log plot, which make it quite easy to decide between, say, two types of architecture or two types of scaling or two algorithms. If one has better exponent or better slope, it kind of gives you much faster decrease in error or loss as compared to another one. That gives you basically ability to decide what to implement when you scale it. And that basically was used when OpenAI was implementing GPT-3 and scaling it. They were using scaling laws to decide how to best grow the system and like what choices to make so it will be most cost efficient. Anyway, so things are actually more complicated than just power laws, and it depends on what tasks you're going to be providing the system, what the so-called downstream tasks are. And generally, it's more of this kind of sigmoid-like curve where you can increase data, for example, on x-axis, or it could be model size. And initially, your error does not decrease that much, but at some point, it may be more like sharper, some transition where things kind of go into this power law region. And then at some point, far in the future, for which you might not even have compute yet, you may reach what people call irreducible entropy. Like if you just kind of learned all of the distribution of, say, text on the internet or the YouTube and so on, you may not be able to improve more. Anyway, so there are all these interesting behaviors, and what we quite interested at, as well as others, is studying particularly kind of sudden sharp transitions in performance. Like the picture on the left is from the famous Grokking paper, where they just keep the model running for a long time, and suddenly it finds good solutions and solution space, and performance improves like, well, phase transitions in physics, practically. Or there are famous examples from GPT-3 when tested on various tasks, including, say, arithmetic. It didn't happen for other downstream tasks, but for arithmetic, it seems to be happening with various systems like GPT-3 as well. You have some slow increase, almost no good performance until a certain point where things drastically change. So basically understanding when does it happen, what it depends on, how to predict it is very important, not just for performance kind of prediction, but there are other properties of these systems like truthfulness of what GPT-3 tells you, or robustness, or interpretability. So all these properties that go beyond just capabilities and belong to the field of so-called AI alignment and safety. You really would like to know if any unsafe behavior of those systems gonna suddenly kind of emerge, and when they're gonna emerge. Anyway, so just to kind of conclude, basically this one particular approach to making systems, AI systems, more general and like truly versatile and few-shot learners seems to be that scaling, though somewhat brute force idea, it seems to be actually working and paying off. So I guess our goal is to now figure out how to do the most cost-efficient and smart scaling. Scale is maybe not all you need, but it seems like it definitely helps, so you need to keep it as one big ingredient. There are various behaviors that I didn't talk about. There could be inverse scaling, so things may get more complicated depending on what you measure and what you're interested in. Like this truthfulness, for example, was getting worse with scale sometimes. And here is a practical, okay, so I'll skip that. I'll just get to this practical question. Because all this recent state-of-art research was happening in mainly industry because they could allow such amount of compute. And it made even the OpenAI CTO Greg Brockman say, well, we think the most benefits will go to whoever has the biggest computer, essentially. The question is, what do we do if we're in academia or we like in non-profit organizations? And there seem to be very interesting recent kind of movements, and many non-profit organizations kind of around the world, and Europe, US, and just international, they work around essentially some Discord servers like Neuro-AI, Lion, so on. We try to collaborate with them. Essentially, the idea is to try to get compute either from private sources or from government-funded supercomputers. So we are currently working on application for the Summit supercomputer, which is second largest kind of in the world. We already did application which was successful for Jewel supercomputer in Jülich Center, Germany, with our colleagues there. Essentially what we're trying to do, we just put together, we kind of try to collaborate with multiple non-profits, universities, well, and some companies as well. So basically I am kind of representing MILA, Université de Montréal, Jülich, and Lion organization. They kind of, as I mentioned, they're working also on large systems, multimodal, like CLIP, extensions of that, large data sets. Neuro-AI is a famous, basically a movement which tries to recreate large-scale systems. They created GPT Neo-X and so on. So there is lots going on. There is big science, of course, in Europe, and Hugging Face, AI Sweden. We essentially discussing including them into these efforts as well. And there are, I mean, as I said, there are interested parties all over the world, and Japan. Basically, again, they interested in joint proposals for supercomputers in order to be able to get the compute necessary to scale systems to the state-of-art performance while not really being involved in like large kind of industry compute like Google and OpenAI. So that's pretty much where we are right now. And if you're interested, there is a set of resources, neural scaling lower class, that I'm teaching and finishing right now. Everything is online, everything is recorded, all the slides that students presented. There are interesting projects there. And there are also a series of workshops that we started last fall in October and December, and we hope to continue them this year. And yeah, so basically you can always find this information on my website, and the links are there. Thank you.
Thank you very much for this talk. A question around the phase transition. So I played around a lot with Instruct GPT-3 and is very impressed by the generality. But when I asked it to what is bigger, 2 or 3, it told me 2. And so I'm trying to finish, like, so what I'm seeing in current like GPT-3 type models is very fine pattern matching, but no reasoning yet. Is there a sense that reasoning is beyond what we can do with scaling, or is reasoning like a part of just scaling up?
Okay, that's a very good question. Yeah, so it's kind of being debated, but I think there is evidence that actually reasoning is kind of emerging. Yeah. Anyway, it's to be more explored and so on. I guess dumb scaling might not be, well, as efficient as smart scaling. But, okay, yeah, I don't have immediate examples, but there have been lots of discussions. Seems like, even like with arithmetic. So indeed, I mean, it's kind of this ability to do arithmetic tasks. It's initially is quite low, and then there is sharp jump in the performance. Those things, there seem to be some emergent behaviors like that. As I said, I mean, it's very far from perfect, and the code generated by Copilot was also sometimes questionable. But yeah, I didn't include some interesting examples also from the student presentations. But bottom line is, there is evidence that reasoning capabilities can emerge with proper scaling and perhaps some additional tricks and proper data and so on. And also there is a notion of the, well, either fine-tuning or basically otherwise like few short learning to change the system output into something that looks more like what you want. So anyway, basically I'm hopeful about reasoning capabilities emerging rather than having to be coded into those systems.
Yeah, that's. I agree with the previous question, and I'm interested in an elaboration of your answer. I mean, you could make GPT-3 do some arithmetic, but at what cost? That, to me, that indicates that there's something missing in GPT-3, including reasoning, knowledge representation of a different sort, and planning to generate the output. Because I've seen examples where the output makes no semantic or pragmatic sense to a human.
So the question is what to do about that. Because one approach is to code it in, planning, and this and that. Or another approach is try to make that kind of capabilities actually emerge at scale by perhaps providing richer data. I mean, there is like lots of discussion that if we ever have enough compute to train on all of YouTube data, then the system probably will accumulate knowledge about all kind of actions, behaviors, including planning and so on. So it's an interesting hypothesis. But why I seem to be personally a bit kind of more into that scaling approach versus like knowledge engineering, because of the bitter lesson that you probably have seen. Indeed, like people started a long time ago with expert systems and just put rules there. Then people put rules how to play chess and so on. And then eventually what really worked was not that. Like when people had more compute, the program basically that beat Kasparov was not the one that had hard-coded rules about what to do with chess in particular situation. And then the same thing with basically DeepMind and self-play. So it seems like if you maybe use inspirations from nature or neuroscience or biology about how to properly scale, it's kind of inductive bias, but it's more of a meta rather than like hand coding the results of that. So that seems to be like a good idea. So you don't want to be encoding too specific information that later on, yeah, it's probably just not gonna survive the test of time. Yeah. But yeah, I mean, there is lots of room for improvement in those systems, and no question about that.
Okay, and here we will end up. I will make brief, extremely brief synthesis. First of all, currently, like majority of models currently are impressive but narrow and task specific. So it's necessary, there is demand to develop an artificial general intelligence, which is, according to OpenAI definition, is highly autonomous systems that outperforms humans at most economically valuable works. And several points that necessary to fulfill in order to get a general artificial intelligence is perform continuous learning, whether transfer or online learning, make model robust to invariance, and be able to generalize example out of distribution, as well as understand neural models scaling laws. Currently existing like foundation models or foundation-like models, it's a really huge models such as GPT-3, DALL-E 2, and CLIP, Copilot, which have billions of parameters, which trained on humongous amount of data. And there are two questions. First one, whether it outperforms the human in terms of capability to learn from my side, because I don't need to get so much data in order to learn something, unlike these models. And in another point, what can do small startups and single researchers? And here emerged and discovered new laws, which shows that model size, dataset size, and amount of computations used for training should be adjusted simultaneously in order to obtain some particular performance of the model. And further investigation of large model discovered, unraveled such type of behavior is grokking, usually really recently reported. And yes, this GPT-3 capability on arithmetic task. From my side, I would add as well that to define general artificial intelligence based on human-centric concepts, it's necessary to also define more appropriately and properly the concepts of cognition, reasoning, and capability to have a general intelligence. What is general exactly?